welcome all of you who have taken the time out of your busy schedules to join us at the Golden Gate Wing of the Commemorative Air Force's monthly dinner meeting, the 28th of August. Our speaker tonight has joined us before and talked on different subjects, Larry Rinek. And rather than my go through his bio, I'm going to let him give a little bit of his own bio. I'm not going to steal any of his thunder. So, Larry, take it away. Thank you.
Okay, thank you. Yeah, I've been associated with the aerospace industry for many decades. My family used to be in the aircraft engine business back in Pennsylvania, early 1900s. My father was a naval aviator. He taught me how to fly. Piper J3 Cub. I had a tour in the Air Force, active duty, and I've been a consultant to the aerospace industries for over 30 years. And so one of my specialties is aero propulsion. It fits right in with the theme tonight. All kinds of aircraft engines. First I was strictly a piston guy, but now I've broadened my horizons to jet propulsion. And so I think it's fair to say everybody in this room has been exposed to jet aviation in one way or another, usually by commercial airline flights. But some of us have had military and close encounters with jets. Do we have any military pilots here with jet time? Okay, good. Maybe some of you maintain jets for one of the branches of the services. But they're certainly a very, very important part of aviation propulsion today. They really dominate most of the markets. And what's left with piston engine is, mid and lower level general aviation is like that. And then there's some turboprop also. So now take a look at that engine I put up there. I have a need for size and power. And this delivers. This is the most powerful aircraft engine ever put into service. Built by GE. It has a Guinness World Book record as the most powerful aircraft engine with continuous thrust delivery on the order of 123,000 pounds. Wow. That's pretty good. And it's been derated for airline use for about 115,000 pounds, so it'll last longer on the wing. So there you are. Let's move on into the next slide. We're looking at the agenda tonight. We see a Westinghouse engine here, which they were not very successful. I'll talk more about Westinghouse's contribution later. So I'll have some introductory remarks. We'll talk about what is jet propulsion. Where did they come from? Came from Europe. What did the US do with this technology? They did a lot of good things with it. We'll look at how the industry transitioned from turbojet to turbofan. In the Air Force inventory, there's almost no turbojets left. There are a few out there, like the T-39 Talon trainer from Northrop is one of the last ones operating with a turbojet. Then we're going to go into the airliner high bypass turbofans used in some military aircraft like the C-5. We'll look at some future trends. So I'm going to take you from the origin to present and beyond. I'll talk about some of the future concepts being discussed now in jet propulsion, summary conclusions, and then I have two exciting short video clips of famous Air Force bombers taking off. One with water injection assist, the other one with rocket assist. So in those days, the turbojets were fairly anemic in power and they needed help. All right, so I'm going to focus tonight on turbojet, turbofan. We'll set aside turboprop for another night. And now when we get to helicopter propulsion, they are turboshaft. They're not considered jet propulsion, with one notable exception. The engineers at Westland, you got to like these guys. They hot rodded a Westland Lynx and added jet propulsion to it in a very clever way. They took the exhaust output. They have two turboshaft engines. They modified the exhaust, turned it into a convergent nozzle, cut the cross-sectional area by 40%. They picked up 600 pounds of thrust, jet thrust, from the exhaust and set a world speed record, still not exceeded, for a conventional helicopter. 1986, they hit 249 miles an hour. And so, yeah, this was over a 15-kilometer course at 500 feet altitude. So you got to like these hot rodding efforts. These are the kinds of things that I like to do to my mobile platforms, do some modifications. Now, notice that it doesn't have to be a gas turbine. Look at all the other variations of jet propulsion here. I mean, some of the examples of jet propulsion were demonstrated really thousands of years ago with Chinese experiments with tea kettles, steam kettles with pinwheels turning up on top. That's a form of jet propulsion. We have, there's a ramjet shown down below, no moving parts, and it works. Now with the ramjet, you have to get it up to speed before you light it off, so that's a bit of a problem. They were used on the tips of Hiller helicopter blades, and they did experiments down at Palo Alto on that. What is jet propulsion? It's all about Newton's laws of motion, the second law and the third law. For every action, an equal and opposite reaction. And so these are also, jet engines are also known as reaction motors. And every one of them has to produce a backwash force, eject gases. A fluid medium could be water, but in jet engines, here we're talking about gases being thrown back, high velocity with acceleration, and they have a mass to it. So the backwash force is defined by this formula here, and it's immediately countered by a forward thrust force. It's just automatic. You don't have to think about it. Kick stuff out the back, you'll be pushed forward. You're not sucked or pulled forward. It's an automatic reaction to the backwash force, and it's neat. It's neat how it works. So the fluid mediums could be all kinds of different gases and so forth. Here's a cutaway of a typical turbojet. You can see where the air has come in compressed, goes in the combustion chamber, they light it off. So you're raising the pressure of the air, then you raise the heat of the air and combine it with fuel, you burn it. That goes into the hot turbine section where it spins those wheels. The pressure's let down, mechanical work is done, and you get this high velocity exhaust out the nozzle. And there's, at the turbine inlet stage, they're now getting over 3,000 F. And they have to especially cool the blades and insulate the blades for them to survive. They actually have to feed in some bleed air from the compressor section to cool down the output of the combustion can or to melt all that hot turbine stage. So this is more of a checklist for engineers. If you're designing this turbo machinery, these are the metrics you've got to meet. And if you're selling these engines to airlines or the military, you better come in pretty good on these attributes if you're going to beat a competitor to get the business. I won't take the time to define all of these metrics for you, but if you're interested later, I could talk to you further about what they mean. Well, I just love this picture of this F-15 Pratt & Whitney F100 engine. See the shock diamonds in the exhaust? Right there. That's a sure sign of supersonic gas flow out the back end. Now, this happens to be a low bypass ratio turbofan. All the fighter engines today are low bypass turbofans. We'll get into turbofan more later, how that's different. Okay, so how did piston aero engines lose the business? These are compelling reasons. Look at the performance gains and maintenance benefits of going to the jet engines. You can create an airframe that's much faster, can fly a lot higher, and just do an altogether a better job. Now, here's one of my favorites, the J75 Turbojet here, and you can mention a couple of the airframes that went into. I happen to have a model of a beloved F106A Delta Dart Interceptor here that had just one J75. Believe it or not, this set a speed record that still stands today. They set the record in 1959 as the fastest single-engine jet on Earth. Hit Mach 2.31 at 40,000 feet altitude. That was almost 1,600 miles per hour. And so there you are. That's a great job by the Convair engineers in creating speed. The purpose of this platform is to get up off the ground and intercept Soviet bombers. And They had unguided nuclear-tipped Genie missiles to fire at the Soviet bombers. Hey, you just had to be in the general area. You don't need guidance. Just blow a nuke into the formation and you've got them. Never used in anger. Just basically test fired once in the Nevada range. Okay, talk about altitude. Let me go back. The turbojets easily could exceed 100,000 feet in altitude on a zoom climb. That was awesome. I mean, you had piston bombers and so forth were good up to about 50,000 feet with lots of turbocharging. So you can more than double that with jet propulsion. Now, they were a handful in the early days. They had terrible fuel efficiency. The materials were not that good. Low thrust. They had to do tricks to get the thrust up, and we'll see examples of that coming up. Oh, they weren't so reliable in the early days. TBOs are now much better. They were, maybe low thousands of hours TBO in the early days. Now they stay on the wing for over 20,000 hours. And yeah, compare that with aircraft piston engines. A military, World War II military fighter engines, R-2800 and so forth, TBO is about 300 hours. They're very overstressed. Then for like an R-2800 that goes in a DC-6 airliner that was nursed and taken care of, that was 2,500 hours TBO in a DC-6. And then you jump up to over 20,000 now with jets. Talk about noise. This is one of the huge, huge drawbacks of jet propulsion. What is the source of this noise? You got the front end and the back end noise. The back end, you got this high velocity, hot gas expelled and has violent mixing with cold air behind the aircraft. That's where that low frequency rumble comes from. Then up front, you've got it's compressor whine going on. It's not quite as offensive. It's higher pitch, that noise. Oh, surge and stall. Let's get into that here shortly. Do not head toward that surge line. Here's where, if you get over to the surge line and to the left, now axial compressor loses its ability to compress. It's not compressing anymore. In fact, you go over there, you get reverse flows. You can have flames coming out of the front of the jet engine instead of the back. So engineers have to get it in a safe operating point. Now, here's a good way to stall an axial compressor is to have too high an angle of attack. And pilots are instructed that if this happens, this is what you got to do. You got to reduce power, put the nose down, get the angle of attack down, and get the airspeed up. And that will solve that problem. So that's the story there on stall. Stall is easier to handle than surge. Surge can be deadly. And by the way, these jet engines make noises. When they surge, you can get a big old bang coming out of there. I'm going to skip over this. This is the thermodynamics of the gas turbine. And we'll go right away to Europe, where really this technology was born. I have to say, Sir Frank Whittle was really ahead of the world in coming up with the concept of jet propulsion for aircraft. He got a patent in 1930 on this concept, and he had working engines on rig tests in 1937. But sadly, he didn't get to fly his engines until 1941-42. The Germans beat them to it. Oheim, working for Henkel, here we are, 1939, got that engine working, and that's running with gasoline. They also tried hydrogen fuel and other fuels. Now, Oheim became good friends with Whittle, and they both migrated to the United States and run into other often. I think they both went to work for the U.S. Air Force. Here's Whittle's story. Sadly, his project was pulled from him by the UK government and given to Rover. What a mistake. Rover did not know what to do with this technology, so Rolls-Royce ended up taking it over from Rover to make these production engines. And they had production jet fighters in World War II before we got our P-80 going. So I have to tip my hat to the English. They also were the most advanced metallurgy in hot turbine sections. They were using nickel-based superalloys before anybody else on Earth. They had an edge there. Okay, how did we get in this business? General Hap Arnold, commander of the Army Air Force, went over to the UK and secured that license from Churchill and brought it to GE. Why GE? They had a lot of experience with turbo superchargers. In Lynn, Massachusetts, they were a logical proponent to run with this technology, and it didn't take them long to have their first Whittle engine running. So Pratt got in much later. It's after World War II, really. They started with the Lean and then developed their own engines that turned out to be very good engines. Westinghouse was brought into the business by the U.S. Navy. The Navy was already using them for marine propulsion, steam turbine propulsion, and it turned out to be not a very good fit for Westinghouse. They struggled badly in this business and had to drop out. I used to work for Manasco Manufacturing, so I was real interested in the R&D they were doing on jet engines in the late 40s. Just 3 engines built. Now, here's a Whittle engine that went into our first jet aircraft, which was totally underpowered and unsuitable for combat. So that production was canceled for the Bell jet aircraft. It's amusing. When they transported this Bell around, they put a fake propeller on the front of the aircraft to try to fool people that it was not a jet. Wow, now they're getting into commercial aviation. This was a big deal when we got into the jet age with airliners. All started with Pan Am, with 707s, and these early models were equipped with Pratt & Whitney J57 twin-spool turbojet engines. Great first efforts. But they found out that they're still short of power and had to go to tricks like water injection, which gave about a 20% boost as long as you had water in the tank. They brought several hundred gallons typically under certain conditions, high takeoffs. And this had to be clean water. It had to be distilled or deionized water, so you don't gum up the internals of the engine. Now, sometimes they would mix it with methanol for antifreeze. And that was a logistics nightmare doing this water injection, but hey, it allowed you to get by with inadequate thrust. And then we'll see a B-47 take off with rocket assist, and that's very dramatic. There's the J-75 right there, which is the bigger version of the J-57. This GE J-47, there are over 30,000 J-47s built by GE and its licensees. There's 6 of them on each B-47 bomber. They were about 5,200 pounds thrust. There was a single spool design. It was kind of antique, but it got a lot of sales. Now we're getting serious with turbofans. Rolls-Royce first one, but not so good. This is not a very good engine. Rolls got, when they got later into the RB211 and the Trent series, they got much better at turbofans. But look at those compelling reasons to switch from turbojet to turbofan. These arguments are so powerful that it really just essentially took over the business and drove turbojets really out of business. Now, for example, how do they get lower noise? It turns out when they get the fan running, it produces a tube of cool air, a lower velocity cool air, surrounding the high velocity jet exhaust. So it dampens and reduces the noise of the exhaust by having that cool tube of air coming off the fan. And the fan provides most of the thrust today. Up to 85% of the thrust now from a turbofan engine is the fan. And the jet exhaust, the jet core, is almost an afterthought. It's just there to drive the fan. Great improvement in specific fuel consumption when they went to turbofans. I think it was hilarious, looking at the technical history of Pratt & Whitney, a book by Jack Connor. They weren't interested in turbofans. How could this be? They didn't see any merit turbofan. We're building great turbojets. Until a customer came, American Airlines, and hit them over the head. Said, look, we're ready to place an order with GE. We want an alternative. What can you come up with? In 10 days flat. Can you imagine designing a new jet engine in 10 days? But they did, and off they were. Pratt was very successful in the turbofan business. Now we're getting into military low bypass turbofans. You can see some of the specs here. This happens to be for the famous B-2 bomber, which follows here. Look at that. First flight out, 1989. Went into service with the Air Force in 1993. In 2013, last year, they got hit 20 years of service. Now, there happens to be 4 turbofan engines buried, 2 on each side. They're buried in these nacelles. And there's an S-turn for the air. It has to come in, go down, and hit the titanium fan blade. You have to hide titanium fan blades. They're perfect radar reflectors. Unacceptable for stealth aircraft. So another thing they did with this engine, to reduce the IR, heat signature, they mixed that cold bypass air with the exhaust. So you cool down the exhaust signature. And the exhaust also exits at the top of the wing to hide it from ground sensors. So they did all kinds of neat stealthy measures, and the engines were part of it. By the way, they had an engine fire in 2010, and the damage was so extensive inside that wing that it is not expected to fly until later this year. I mean, it took years of repairs if you have an engine fire in a B-2. The beloved B-52 H model. Here's where they upgraded. The G model was the last one that had the wet takeoff turbojet. Now we've got real turbofans with a bypass ratio, kind of low bypass, but they had now a much more powerful, a higher capability bomber. There was also cleaner and quieter. So this was very smart to upgrade to the turbofans. Now, but some of you who've tracked B-52 history may have noted that 2 or 3 times there have been proposals to re-engine this very aircraft with 4 bigger turbofans, like Rolls RB-211s. And there were serious efforts looked into that, but the Air Force said, we've got other uses for this money. So they've been languishing with these antique turbofans. There's no chance of getting new ones at this point. Although there have been many, many other upgrades, all new cockpits in the B-52 and new weapons carrying capabilities. Now we're moving into the favorite engine for airlines. They have tremendous performance. Look at those bypass ratios. How do you define a bypass ratio? It's the ratio of the air going through the bypass ducts to that going through the core of the engine. So they're 8 or 9 now, and they're planning to go up to 12. That has tremendous thrust benefits. Look at the thrust ratio now, the fan doing 85%. That's going to go up with a new geared turbofan. But look at the radar cross-section. Look at that fan there. By the way, the fan on the GE 90 model on my cover slide is almost 11 feet in diameter, or that fan. What a huge radar reflector that is. So if you want stealth, you're not going to get it with this, but you have to have this. If you have a C-17 or a C-5 aircraft for the Air Force, you need the thrust that fan gives you. Now this is interesting. I mentioned geared turbofans. The concept there, we're going to see an example of one in a few slides. The idea here is through a gearbox, you put a bigger fan on and turn it slower, but now the core of the engine can be downsized and turned faster. And there's about a 1/3 reduction, so there's 3-to-1 reduction. That is to say, the fan turns 1/3 the speed of the small core of a geared turbofan. But look what happened when you could take off and the pilot's not careful taking off with a big turbofan engine, especially if it's titanium blades. The gyroscopic effects are enormous. So the pilots are counseled, please roll on the throttles gradually. If you go too fast, the gyroscopic effect can take the aircraft right off the center line into the weeds. So you have to manage that thrust with a big turbofan. wow, look at the future of jet engines, make them electric hybrids. Awesome. There's all kinds of studies going on with this right now. They got federal funding, Georgia Tech, to try this concept for a 50-seat regional passenger jet. And so the idea is, take off and climb out. You'd be generating power and storing it on board with, lithium-ion or some chemistry. Turn it off at altitude and just run on the fan electrically. And you have to have motors to run the fan in here. There are thousands of horsepower. And just cruise and cruise and cruise with zero emissions across your entire flight path until it's time to descend. And you fire up your engines again, and those engines will bring you in for landing, all the while recharging your batteries. So that's the concept. It hasn't been demonstrated yet, but these are the kinds of advanced studies going on right now in the propulsion world. Just as we've seen hybrid electrics make a big splash in the automotive world, cars and trucks, it's now coming to aero propulsion. Now look at this high-tech stuff that's in development or already just introduced with these special materials, super high bypass ratios. I mentioned 12, how about 15? There's a lot of tricks in the trade that people are working on. Now Rolls-Royce, it's interesting, they publicly disparaged Pratt's work with geared turbofans, and then they said, well, you know what, this makes sense for the biggest turbofan. Our biggest Trents going forward are going to get that new architecture. There's some compelling advantages. If you can make that gearbox ultra reliable, you cannot have gearbox failures like you see on helicopters. In this application, you're carrying passengers. So they're going to have a special attention to the gearbox. Big fans, how big do you want? I mean, here, they're going to be so big you can't hang them under a wing. I mean, you're going to put them above the wing now? I don't know. But or have extremely tall landing gear to bring the airframe up for fan clearance. Now this is interesting. Here's Blisk. Here's a production Blisk that's now in the Gen X engines, which are flying the B787 Dreamliner and the 747-8 Freighter. Both of them were released by the FAA for deliveries last fall. So this is really hot stuff. You can, with a Blisk, you got blades and the disc combined. You can machine them. You can cast them that way. There's different ways to make the Blisk. You can even try welding on the blades. I don't recommend that. There's a failure mode right there. So that's a glimpse of what's the future in jet engine, jet propulsion. So to summarize, we saw the work in Germany and then England, came to the US, here are the key players in the US. Today it's really just GE and Pratt really run this business. And these others have kind of dropped out. I mean, Wright had no idea what they're doing with turbojets. The J65 is a total failure. Lycoming. All right, Allison. Allison was successful at being a second source. Allison built most of the GE aircraft engines. In the 40s and 50s, that was the government's doing. I said, okay, let's hand this over to this shop in Indianapolis, at Allison. And they built a hell of a lot of them to GE spec. And they let GE go on and do new engine programs that are more developmental. So we saw the advantages of jet engines over pistons. There are a lot of advantages there. I mentioned before the vibration and low vibration advantage of jet engines, but they are susceptible to vibration problems. In fact, the one and only time I faced in-flight shutdown in a commercial airliner of a jet engine was due to vibration over the North Pacific. This was a Pan Am 747-100 or 200, Pratt & Whitney JT9D engines, Narita, Japan to SFO. The engine went red line on vibration, one of the four, over the North Pacific. And then they had to windmill the engine. They had to shut it off and let it windmill. The drag is so high from a windmilling turbofan engine, they would never make it to SFO. So they had to divert to Hawaii and Honolulu and change plans and change engines. So that is pretty rare today. It's extremely rare for in-flight engine shutdown with modern turbofan engines. Some of you remember the piston airliner days. Now that was really, there was some excitement and drama. I mean, I'll never forget a takeoff in a DC-6 American Airlines from Hartford, Connecticut in the 50s. I had a window seat, and these are all 4R2800 Pratt & Whitney engines. The one next to me at the window, the number 2 engine, caught fire on takeoff. You know, it was black smoke. It was like an oil fire or something. They had to reject the takeoff. We had to get it in another plane. But this is the drama. This was real flying in the 50s with piston airliners. There was no end to the drama then. The sound, the romance, the smells of piston engines. You got none of that drama today with turbofans. I guess we kind of like it that way. When you're up at altitude, it's just sitting there humming, doing nothing outside the window. And we prefer it to be that way. But piston engine enthusiasts, and a lot of us out there, we miss that drama. One of the great authors of Graham White on historical developments in aircraft piston engines, he dismisses these things. He said these are glorified hair dryers. What you're looking at here. So yeah, if you stand behind one, you'll get dried pretty fast. You'll also be tumbling down the tarmac with the backwash force. All right. So we've explained why turbofans have replaced turbojets. There's some interesting future goals that are still open to the designers. Wouldn't it be neat if they can make a turbofan tolerate a flock of birds? We saw what happened with Captain Sully Sullivan in his US Air, I think it was an A320 that had to go down in the Hudson River. There the engines, both engines, were flamed out. And he kissed it in nicely. We saw the videos of how he came down and kissed that in perfectly. Here's what happens, folks, when you lose jet engine power. Immediately, it drops down out of the belly of the aircraft is a rat. A ram air turbine immediately, automatically drops down and gives you electric power and hydraulic power so you can run the avionics and keep the hydraulic controls intact so you can still fly it with no main engine power. It's a great safety feature. Now here we are. Here's that geared turbofan. Now in development. It's going through FAA trials. It's not yet released for production. But they're building engines, Pratt's building engines here with their MTU partner in the range of 15,000 to 33,000 pounds thrust. Bypass ratios around 9 or 12 to 1, and fans up to 81-inch diameter. So that's coming on the horizon. I'll just briefly mention this. I won't go through all of these programs, but just a sample of where the business went in turbojets and turbofans. U.S. only here, and military versus civil. There's more engine models than these, but these are the key ones. And so with that, I think we're going to go right to the dessert course, the jet engine takeoffs. First, we're going to do, let's hide this document, escape. And we'll close it. And we're going to go right to the video. This was from the movie Strategic Air Command. You can get this at Amazon.com. I think it's a classic. They also show a B-36 takeoff, but the B-47 takeoff is very dramatic. It was filmed at MacDill Air Force Base in Florida, which was an operational base in the 1950s. We're going to see the great Academy Award-winning actor Jimmy Stewart at the controls, the B-47. Now, you'll see him call out RATO on. The Air Force liked to use the term RATO, rocket-assisted takeoff. The US Navy preferred JATO, jet-assisted takeoff. And actually, the Navy pioneered this technology with flying boats in World War II. And they typically use 1,000-pound thrust Aerojet rocket bottles, solid-state rockets that are expendable. So let's watch. This is MacDill, Florida, Tampa, Florida.
coming close.
Okay, Dutch.
How about you, Rocky?
Roger.
McNeil Tower, that's 5024. We're ready to go.
5024, you're clear for takeoff.
Roger, 5024. Rolling. Torpedo.
Now, that was the B-47B model. The next variant was the E model, like this one, had much more higher production. But in the B model, you notice they had 9 rocket bottles per side. And I talked to the air crews, B-47, they had to demonstrate one of these takeoffs every year as part of your qualification to fly the B-47. Show you can do it. But it was not routine to use the radio. Now, the E model, get this. They got rid of the internal ones and put an external rack, a horseshoe-shaped rack, underneath the belly, carrying 33 Aerojet rocket bottles. Wow. Awesome takeoff power. Wow, wow, wow. And then the rack was droppable, so they get past the end of the runway and drop the rack, and they'd recycle it. So that was nifty. This is when we had these anemic, low-powered turbojets. They needed help. So there you are. Now,
I understood that Fat Albert was the last plane to use JADA. Fat Albert with the Blue Angels.
C-130. Okay, yes, it's.
And they ran out of bottles. They used them all up.
Oh, okay.
That was it.
Yeah. Yeah, they're neat. All right, now let's switch to a water-injected takeoff and see what that looks like. I'm going to go out and load up the plane. This was a nuclear-capable intercontinental strategic bomber. Notice the white belly paint job. That was to resist nuclear flash effects. Carl Malden. Yeah. Check out this landing gear swivel. The only aircraft I know can do this. Plus or minus 20-degree swivel landing gear. I'll tell you why they did that after this clip. Crosswind landings, exactly. Check out that smoke. Notice it taking off with the nose down. Okay. Let me explain the landing gear. The special problem that B-52s had is this great big tall tail fin, but a tiny little rudder. It's only like, the rudder was only like 10% of the dimension of this tail fin, where normally it would be 25%. So this thing, the B-52 had no rudder authority. What are you going to do in a crosswind landing? You didn't have an ability to handle a crosswind landing. So instead, you could come in at a cocked angle, say 20 degrees off center line, pointed into the wind, and land straight in on the center line. Nifty. So it was also good for parking back on the apron. You could back it in and stuff and do some nice maneuvers with that landing gear. So B-52 engineers at Boeing in Seattle had to get a little clever in putting features in there that would meet the Air Force needs. So that concludes the program. I hope you liked it. I'm open for questions from the audience, and I thank you for coming. Yes, sir.
I have a question. So these early jet engines were very smoky.
Inefficient.
What caused the smoke, and when did we get rid of that?
Yeah, the combustion conditions were not ideal. They were just happy to get thrust. Smoke was secondary. But let me tell you about water injection, what happens there. It's a special case where the engine controller is actually fooled. When the water, you've got heat of compression is removed, the water sprays ahead of the compressor section. So it's removing heat of compression as it goes through. So it cools and densifies the air. Now it gets to the combustor section. The engine controller says, oh, I'm getting more air. Let's turn on more injectors and dump more fuel in. No, you're not. No, the air-fuel ratio is now all screwed up. It's extremely rich. That's why you have so much unburned carbon going out the exhaust. But you know what? You want that because thrust is proportional to the mass flow through the machine. And so, hey, more carbon, more fuel, more water. Hey, just throw it in there and run it to the machine. You get more thrust temporarily, and that's why you see extreme smoke with wet takeoffs. Not politically correct today. You could not do that and get by with your neighbors, putting out that kind of air pollution. Yes, Gil?
The B-47 takeoff with a nose, I mean, even parked, it's taxiing around nose high.
Yeah.
It took off nose high, so that the angle of attack on the wing would be correct, and then the it's a question, not a statement. And then the B-52 looked like it was just the opposite.
I'll tell you how.
Takes off nose low.
Let me explain how the B-52 got away with that trick. The Boeing engineers built into the wing roots a 6-degree angle of incidence, just sitting level on the ground. It was already cocked up 6 degrees. And the B-52 had a built-in angle of incidence, so you can actually take off a couple degrees down and still have a positive angle of attack. You get no lift without an angle of attack. If you look at the lift curves, you get nothing at 0 angle of attack. You got to have some angle going into the prevailing wind. So that's one of the neat things about the B-52. It can take off like that. I interviewed pilots like the famous Colonel Joe Cotton, test pilot for the Air Force. He said, like flying the B-52 is like flying an elevator. Just goes up and it goes down. No dramatic, it's not like a jet fighter rotating at takeoff. None of this business. All right, any other questions? If not, yes, Guy.
I noticed at the Hiller Museum some early jets had the stator blades were a variable pitch. They were all like on a rack and pinion kind of thing, so they would all change pitch together. Mm-hmm. Is that still used today? Did it come and go?
Well, it turns out that now here's GE J79 engines example of variable geometry. They went with a single shaft design, but with variable geometry stators. They could also vary the nozzle area in the back. So yeah, variable geometry was coming in. That was GE's answer to Pratt's dual core, dual shaft design, which was another way to optimize flight. So yeah, variable stators was definitely there. But then that was tabled for decades. It's too complex. We're not going to do that again. But you know what? You saw on the list of future advanced features. It's being looked at again. Let's look at it again, see if we can squeeze a little more efficiency out. I mean, the engineers will kill to get another 0.5 or 1% efficiency in fuel burn with turbofan engines today. They're so highly refined, requires extreme efforts.
Explain what the purpose of the stators is.
Well, the stators are in there. You got rotating, yeah, the stator acts as a diffuser in compression turbo machinery. It redirects the airflow, acts like a diffuser. So the compressor does not work without those stators there assisting.
Why didn't Boeing go back and put a bigger rudder on the tail rather than change the landing gear, which is not cheap?
That was one of those mods that was going to be unobtainable. You know what they did? When they went from the F model to the G model, they actually sliced off a huge chunk. Several feet of the top of the tail fin disappeared on the G model and H model. So now you got what? Now you've got less rudder area back here. So I don't know how to account for that. But they retained. You still have them today in the H model. The steerable landing gear for crosswind landings. Maybe they thought the loads would be too high on the empennage back here of having an extremely tall tail fin with a big old rudder on it. There's strength and structure issues that they had to be sure were within limits.
You know if that aircraft that size has a yaw damper on it similar to all civilian aircraft?
Funny you should mention the B-47 was one of the very first, if not the first, aircraft to get an automatic yaw damper in there. They had vacuum tube servo amps and actuators, and so it stopped this aircraft from doing these sickening Dutch rolls. All swept-wing jets are susceptible to Dutch roll. You start with a roll, and then that induces a yaw. Roll, yaw, roll, yaw. You got to damp that out, and it does it automatically very fast. The pilot doesn't have to think. Just stops the yaw with the damper back here with the rudder.
Standard pilot doesn't have to think.
Yeah, I mean, this is what you want. You don't want the pilot to have to think too much.
To begin with, right?
Right.
Yeah, so there you are.
Exacerbating the problem.
Okay, thank you all for your time.
Thank you.